Welcome to our Project 3 presentation by David York and Matthew Hitch. The design team was tasked with modeling a parabolic pin fin to find the optimum length using copper, aluminum, and stainless steel as the materials. This proved to be difficult to do with a theoretical analysis due to the parabolic shape of the fin. The team equated the parabolic fin with a cylinder as a close approximation in size and performance. The equations shown below were used to find the length required to reach ambient temperature and heat transfer rate. It was assumed that there was 1D conduction, steady state conditions, and that radiation is negligible. Shown here are the thermal conductivities of each material. The base diameters used in this analysis are 80% of the actual diameters to account for the pin being a parabola. The table shows the cross-sectional area and the perimeter of the fin. Here are the results of the team's calculations. Note that as the conductivity of the material increased, the fin length decreased.
Having completed the theoretical calculations, the team proceeded to evaluate each of the 9 cases in ANSYS. First, we solved for the equation of the parabola using the desired infinite length and diameter. Next, we modeled the fin in NX using a law-defined spline. We then exported this model to ANSYS using a step file. Once the model was in ANSYS, the team generated a mesh for this geometry. We then applied the convection and temperature boundary conditions. This yielded a number of useful figures. The team generated 4 plots for each of the 9 cases. In the top left is the plane mesh. In the top right is an isometric temperature contour plot. In the bottom left is a plot of the isothermal surfaces, and in the bottom right is a plot of the heat flux at the base. Note how the isothermal surface plot illustrates the questionable nature of the 1D assumption. When the team compared the results, we found that the temperature at the tip of the fin was consistently around 7% above the ambient temperature. The heat exchange error was higher. This was a result of there being significant estimation in both the theoretical and finite element approaches. The team finds that the theoretical model consistently yielded fins that did not reach the ambient temperature at their tips. However, this model could be used to generate a lower bound first approximation of the infinite length. From there, an iterative process with NX and ANSYS could be used to find the true infinite length. It should also be noted that for larger diameter fins and for fins made of low conductivity materials, it would be desirable to find an alternative model because the 1D approximation becomes less valid with higher diameters and lower conductivities.